Today, I am going to introduce you the concept of dimensionless pressure drop solution by using the Darcy's equation. So we all know that the Darcy equation is Q naught equal to 0.00708 times with KH and the pressure drop PE minus PWF divided by mu naught P naught ln RE over RW. Rearranging, we get PE minus PWF divided by Q naught B naught mu naught over 0.00708 kH equals to ln RE over RW. The units for RE and RW are feet, and we can cancel those units, making them dimensionless. We also know that the units for PE and PWF is PSI, so this term here should be PSI as well. Cancelling the units would also make them dimensionless. Now moving on, we know that RE over RW equals a dimensionless term. So it can be written as RE over RW equals to RED, which is dimensionless radius. Therefore, equation 685 can be written in a dimensionless form as PD equals to ln RED, where PD equals to PE minus PWF over Q naught B naught mu naught over 0.00708 kH. Next, in transient flow analysis, which is unsteady state flow, PD is a function of dimensionless time and can be defined as PD equals to Pi minus P, function of radius and time, over Q naught B naught mu naught over 0.00708 kH. Where dimensionless time equals to 0.000264 kT over porosity mu Siti r squared W. This equation is known as the mother equation or the dimensionless pressure drop solution. To solve for PWF, the dimensionless time is a very important equation, and memorizing it would help us solve dimensionless problems much faster. Now that we have known the dimensionless concept and the dimensionless pressure drop equation, let's take a look at the diffusivity equation, which is this. Where 1 over n is this. Whereas for dimensionless pressure, we have several dimensionless variables such as Td, which is known to be 0.0000264 kT over porosity mu Ct r squared W. When we have PD and RD, and we can substitute those variables into the diffusivity equation. To form this, Van Avenetian and Hurst evaluated several values of RED over a wide range of values for TD, and then they are tabulated by Chaitis and Lee to solve for infinite acting reservoir and finite radial reservoir.
In this section, we are going to learn what is an infinite acting reservoir and what is a finite acting reservoir. Assume that a well is located in a very large reservoir and producing at a constant flow rate. When we produce, a pressure disturbance is created in the reservoir. For now, we can see that the pressure disturbance has yet to reach the reservoir boundary, and therefore we can say that the reservoir boundary have no effect on the well pressure behavior. During this period, it is said that the reservoir is infinite acting and the flow is unsteady or transient. As the pressure disturbance reaches all drainage boundaries, it ends the transient or unsteady state flow regime, and a different flow regime starts, which is the pseudo-steady state flow. In this period, the reservoir is said to be finite acting. During this semi-steady state flow, the change in pressure with time becomes same throughout the drainage area as shown in the graph.
So to recap, an infinite acting reservoir is a reservoir with no apparent outer boundary limit affecting fluid flow. Its dimensionless pressure is a function of dimensionless time, and the dimensionless external radius is equal to infinity. There are three simple steps in calculating infinite acting reservoir. First, calculate the dimensionless time TD using equation 6.87. Second step, check the TD value and use the appropriate condition for dimensionless pressure, or we can read the value directly from the PD versus TD table. The last step, find the bottom hole pressure using equation 6.97.
For a finite radial reservoir, the reservoir boundary influences the pressure response in the reservoir as the pressure disturbance has reached the boundary. Therefore, dimensionless pressure is a function of time and radius. There are also 4 easy steps to solve for finite radial flow. First, calculate the dimensionless time. Second, since PD is a function of time and radius, we need to calculate RED, which is the external radius or the wellbore radius. Okay, the third step, we can determine PD from this table or from the following equation. Lastly, solve the pressure at the desired radius using equation 697. And then you have it. Easy steps to solve finite reservoir problem.
So, in this video, we have learned about the diffusivity equation and its dimensionless form, as well as the dimensionless pressure drop solution. We have also learned what is an infinite acting reservoir and what is a finite acting reservoir. And last but not least, we have learned the steps in calculating the bottom hole pressure for infinite acting reservoir and finite acting reservoir. Thank you.